couple of things to do today that will get us out of that awkward first chapter and get us ready to go on and actually look at some matter, look at some atoms, do some real chemistry. Here are two words that if we are still concerning ourselves with the world of measurements, here's two words that kind of get thrown around quite a bit. And because modern language is imprecise, oh, there you go. The meaning of these two words in general use has been blurred. That these two words might seem like they're interchangeable in just regular conversation, but they mean two completely different things. Completely different things. Okay, if I asked you, what time is it? What time is it?
9 o'clock.
It's 9 o'clock.
3 seconds.
Oh. I had a first answer, and then I had a second answer, and my second answer improved on the first answer, right? Because it went from being 9 o'clock to being 9 o'clock and 2 seconds. Which one did Mabel improve? Did she improve the precision or did she improve the accuracy? You improve the precision. Precision tells you how much detail is in your answer. When you look at data sets, another way of thinking about precision is how much agreement do you have within your own numbers? So that when we take a measurement, and you're going to start doing this in lab next week, when you take a measurement, just that one time, if I say, here's an object, go weigh it, and you go to the balance and you weigh it, you've come up with an answer. You've come up with one answer. Well, what if you did it wrong? Now your answer is guaranteed to be wrong. So we ask you to do measurements in replicates. We'll say, go ahead, measure the mass of this object, but do it 3 times. And if you can, give it to somebody else and have them do it as well. And now you've got the answer multiple times, and you can feel kind of comforted when those numbers agree with each other. Okay, so if we asked you all to measure an object and you all got exactly 10.00 grams, then we would feel fairly confident that that was the answer. So the precision is how much detail is in the answer. Also clumped in with precision is how much agreement is there between values in your data set. So when you reproduce your experiment, do you get the same answer again? Okay. So that's precision. What's accuracy then? If precision is just the amount of detail in the answer, what's accuracy?
Is that like how close it is to what the answer like should be?
Yeah. It's how good of a job did you actually do at measuring the value? So accuracy is how close did you get to the real answer? So if we ask the question again, and I ask, what time is it? And your answer is, it's 9:05. That's a reasonable answer. But if you told me that it was 9:04 and 37 seconds, that would be a more precise answer. If you told me that it was 12:01 and 18 seconds and 34 milliseconds in the PM, then your answer would be even more precise, but it would be wildly inaccurate. You've given me something with lots of detail that is nowhere near the actual value, the real value. So accuracy and precision don't have to be tied to one another at all. You know, in the real world, what we want is accurate information that is as precise as possible. So if we can have both, that's great. If you can only have one, which one would you want?
Precision.
So you would have, when you ask me what time it is, I would say it was 12:01 and 37 seconds.
Okay.
And 18 milliseconds. No, you go for the accuracy. If I say it's about 9:10, I'm 5 or 6 minutes off, but does it matter?
I guess I was thinking along the lines of like, if in science, you probably want precision.
No, I want to get as close to the real answer as possible and worry about improving my experiments and get the precision later on.
Okay.
That's what I would do.
Thanks.
Okay, all right. So this one, improving that number, all comes down to experimental design. Asking the right question. This one, there's a component of math in there. So when we use numbers and we measure precision, we have to count units of precision. Units of precision go by this other known title. Significant figures. You've all seen them. You all hate them. We all do too. But they have a point. That there is a point at which you ask your calculator a very simple, imprecise question, and then your calculator gives you a 10-digit long answer with now 8 decimal places. That's precision that's made up. And you're not allowed to use it. So all that significant figures do for us is we use them to round the final answer in anything that we do. We just round that number down. So significant figures, these guys represent the amount of precision that a measurement is allowed to have. So these represent the measured precision in a number. Okay. And all you have to do is count how many digits there are in the number that you're looking at and count them up, because that's your number of significant figures with an asterisk. What's the asterisk when it comes to significant figures? There's something that we have to take into account.
There is difference between multiplication and division.
So we're going to get to that very, very soon that you use significant figures slightly differently when adding and subtracting than you do when you're multiplying and dividing. But when I'm counting the significant figures in an actual number on a page, if all I had to do was count all the numbers up in the question, that would be almost too easy. What is it that makes significant figures feel like they're hard? You have to make a decision. What's the decision based around? The question is, do zeros count? When it comes to significant figures, all, I'm going to call them real, all real numbers, that's a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, and a 9, they all count. They are all significant. Zeros can be significant, but only if they do one of these two things. Zeros are only significant if. Do we know what any of the cases are? Yeah, go ahead.
In between two non-zero numbers.
Yeah, if they're sandwiched in between two real numbers. Anyone that's a math major is going to be screaming at me for using the word real for numbers, because there is an actual thing in math called real numbers, and this isn't it, but you know. So a zero that occurs between two real numbers counts. What else? There's another one. Go ahead.
It's after the decimal, but it's also after non-zero.
Yeah, so that one's actually kind of two things, isn't it? But so there's only two rules. One of them has two clauses in it. That the zero is behind the decimal place and following a real number. Okay? So I'm going to write some numbers on the board, and we're going to figure out how many significant figures we have in those numbers. Right? $124. How many significant figures are in 124? All real numbers are significant. So the 1 is a significant figure, the 2 is a significant figure, the 4 is a significant figure. How many is that? Say it out loud. Okay. What about that number? 1,204.
4.
That's 4 significant figures. It has a real number, there's a 0, and a real number. This leads me back to these two clauses. Is the 0 between two real? Yes, it is. Okay, so it counts. That has 4 significant figures. If I rearrange these numbers, have I changed the impact on my precision? Yes, I have. Yes, I have. Because this 0 now does not fit either of these two descriptions. So this number has a 0 in it, and it's not sandwiched between two numbers, and it's not behind a decimal place. Therefore, that 0 doesn't count. There are only 3 units of precision in this number. So this number is less precise than that number. If I wanted to represent, if you had been told that, no, really, that really is a 0. I've measured it. I really measured it, and it really is a 0. My value is 1,240 milliliters. Guarantee that's the real answer. I want you to include that digit right there as being real. How do we do that? We do this really awkward thing. We put the decimal place there. If we put the decimal here, then the decimal place legitimizes the numbers. And it means that that one now counts. So that goes back up to being 4. You are not going to see this, okay? You are not going to see a decimal point without a number behind it. But I'm telling you that it exists. I'm just telling you that it exists. Okay, so this is rarely seen. You hardly ever see this. Okay, let's look at some numbers that have perceived perception because they have decimals. Zero 0.00124. How many units of precision? How many significant figures does that number have? Okay. Who else thinks it's 5? Who thinks it's 6? Oh, there are 6 digits on the page. Okay. Who thinks it's 7? If you think it's 7, you're not paying attention. 5, 4, 3, 2. That's a 0. And that's a 0. And that's a 0. Okay. So every time I see a 0, I have to ask myself, is it one of these two cases? Is this 0 between two other numbers that are 1 or 2 or 3 or no? And neither is that one, and neither is that one. So these zeros are not between two other numbers. Are they behind the decimal place? 2 of them are. Are they behind the decimal place and following a real number? No. Because that's not a significant number, and that's not a significant number, and that's not a significant number. The first real number here is that 1. I have 3 units of precision. What if I did it this way? That's got a 0 in it. How many significant figures do we think are in this one? 4 sounds right. Let's check. There's a 0, so I don't have to worry about the other the regular numbers. Okay, but there's a 0. Is that 0 sandwiched between two other numbers? No. Is it behind the decimal? Yes. Is it behind the decimal and following a real number? Yeah. So this gets to be 4 significant figures. And that's almost all there is to it. So some numbers are more precise than others, okay? So if you were told that you had to add these two numbers together, this number is more precise than that one. And so adding them together, it seems a little bit unfair. Like if we say, okay, what we're going to do is we're going to do a group project, and this side of the room is going to measure something out as accurately as they possibly can, and this side of the group is going to measure something out as accurately as they possibly can, and we're going to combine the samples together at the end and add them up, and however close your group number is to the final answer, that's how much I'm going to pay you. And you guys have access to a 4-figure balance, a scale that measures to 4 decimal places. And you guys have access to a bulk balance that measures to 1 decimal place. You do the best job you can, but you only get that 1 decimal place of precision. You guys, you got 4 decimal places of precision. And now when I add your numbers together, these 4 decimal places and this 1 decimal place add together, and all of this precision here is lost. And the amount that I pay you guys is reflected on these guys didn't do a good job. They didn't do a good job because they weren't given the right tool. Okay, so you get screwed because they didn't uphold their half of the bargain. Okay, precision is about how well was I able to measure stuff. It's about measurement. And if we mix numbers together, our final answer is only as good as the most imprecise value, okay? When you add or subtract, your final answer is only allowed to keep the precision of the answer with the smallest number of decimal places. A couple of years ago, I took one of the classes completely online, one of the healthcare classes with chemistry. And when I was writing the final, I thought, as an opening question, I will give the students something easy to do. And I kid you not. The opening question on the final exam is, here are two numbers, add them together. It is the lowest scoring question on the final exam. Like 17% of the class get it right. I'm not kidding. Take these numbers and add them together. Question number one on their final, and it's the lowest scoring question on the test, because by the time the final had rolled around, they'd all forgotten this. But if I give you two numbers, I give you, let's go, who's looking at me? You're looking at me. Just start saying numbers.
7, 2, 5, 0, 4, 8, 7, 0. Uh, 6, 4, 9, 1.
Add those two numbers together. If these two numbers represented masses, somebody did a really spectacular good job of measuring this mass, and somebody did an okay job of measuring this one. And when we combine these two masses together, do you think I'm allowed to keep these digits? No. No, because we don't know what number belongs here. I don't know if that's a 1 or a 2 or a 9 or an 8. I don't know what number that is. I have complete uncertainty of what that number is, because it's missing. Which means when I add these two numbers together, I'm only allowed to keep this much. This is the amount with the smallest number of decimal places. So 9 and 4 is 13, carry the 1, makes that a 5. 6 and 5 is 11, carry the 1. There you go. 731.53. All of this work is lost. The person that puts in all of that effort, your work is lost because you've combined it with something that was imprecise. Okay? Adding and subtracting limits you to the smaller amount of decimal places. That make sense? Okay. Adding and subtracting is tangible. You can kind of conceive of, oh, I'm going to take a measurement of liquids or masses and just combine them. I can do that in my head and imagine it. Multiplication, not so much. In multiplication and division, the final answer keeps the same precision as the value with the least significant figures. So if I'm multiplying two numbers together, whichever one of those numbers has the least number of significant figures, that's the number of significant figures that are going to be in your final answer. Okay? Start throwing numbers at me.
2, 5, 9, 8, 0,
I can ignore you, 0.
1, 7.
You might need a calculator. Unless you know your 17 times table. Did anybody learn a 17 times table? No. It's 325.98. How many significant figures are in 325.98? That has 5 significant figures, and multiply it by 1.7, which has 2 significant figures, which means my answer is going to have 2 significant figures. Do the calculation on your calculator. Do not round down or round up. Just give me what the calculator tells you. Who's done it? Anybody done it? Somebody needs to do it. 550, okay. 554.166. Okay, we can all agree that that does not have 2 significant figures. This, and this, you're not allowed to keep. Because you've taken a very precise number and you've multiplied it by an imprecise number. The painful thing is we also have to get rid of that one. Because I'm only allowed to keep 2 significant figures. So to the best of my ability, the answer to this question is 550. Do not round your question, the numbers in your calculation down in the middle of a calculation. If you have to find a number and then use that number to find another number and then use that number to find another number, and every time you round them down and whittle away the number of significant figures, you will end up with nothing at all at the end. Keep all of the imaginary precision that your calculator tells you, and then apply the significant figures at the very, very end. Do it once, do it at the end. Okay? All right, let's do some calculations. Because we're going to apply this to something that's been itching at us for a little while now. Yes, I just made those numbers up. Okay. Density. Density is characteristic of all pure materials. The elements that are on the periodic table, one of the things that we're going to learn next week, or maybe Friday, is that elements contain only one kind of atom. So they are pure. They're as pure as you can get. So copper, which is on the periodic table, is a metal, has a characteristic density. I think it's like 6.9 grams per milliliter, something like that. Aluminum on the periodic table is a metal, pure, 2.7 grams per milliliter. Gold, 19.3 grams per milliliter. So density, so with your eyes closed, if I had two cubes that were exactly the same size, and one of them was gold and one of them was aluminum, and you were blindfolded, like on a TV quiz show, and told, if you can guess which one's gold, you get to keep it. That is easy, because gold weighs 19.3 grams per milliliter, and aluminum weighs 2.7 grams per milliliter. So it's like 8 times heavier, the gold one. So in your hand, the two objects, the gold one would be much, much heavier because it's more dense. Be very, very easy to figure out. Density is mass per volume, and it is usually measured in grams per milliliter. When I look at the question gives me a mass, and it's in grams. And then it gives me a volume, and that volume is not in milliliters. That volume is in liters. How many milliliters were in a liter? 1,000. The answer is always 1,000. There are 1,000 milliliters in 1 liter. So before I put my mass and my volume into this equation, what I'm going to do is figure out how many milliliters do I have. So I have 0.5 liters, and my conversion factor is that 1 liter is 1,000 milliliters. Okay, let's think, do I divide this number by 1,000 or do I multiply it by 1,000? Here's how you figure that out. You keep the units in. It's a thing called dimensional analysis, and you can do it with the whole calculation, but I like to break it down into smaller things, especially at the beginning of the term. Currently, this answer is in liters. I want my value to be in milliliters, right? So I need a conversion factor that expresses liters and milliliters. And I just said that 1,000 milliliters equals 1 liter. And I want liters to go away. If I put liters at the bottom, this liter and that liter are going to cancel each other out. So 1 liter is 1,000 milliliters. That's my conversion factor. The milliliters stay on top, and the liters divided by cancel each other out. I'm going to multiply 0.5 times 1,000 is 500. I have 724.9 grams divided by 500 milliliters. Whatever that number is, whatever that value is, take those two numbers, divide them by each other. That's your answer. And your answer is going to be a number and then a dimension, a unit. And that unit is grams per milliliter. And then we'll figure out how many significant figures we had, and we'll round that number down to the amount of digits we're allowed to keep. So 724.9 divided by 500 equals, a bit louder, 1.498. I'm glad that you gave me lots and lots of digits out of your calculator here. Anybody else get that number? Yeah, good. Good. Reproducibility. All right. Let's look at the question. How many significant figures are here? How many significant figures are there? The rules aren't on the board anymore, but this number has 3 zeros in it. Does that first zero count? No. Does that zero count? Is it sandwiched between two other numbers? No. Is it behind the decimal and also behind another number? Yeah. Yeah. Yes, it is. Is this behind the decimal and also behind another real number? Yeah. Oh, yeah, it doesn't mean immediately behind, it means just behind. Okay, yeah. I'm glad that came up. Yeah, it's just behind at some point. So this has 3, which means that 1.4498 has to get rounded to an answer that gives me 3 significant figures. That's my last unit of precision right here. But that 4 is closer to being a 5 than it is to being a 4. So I have rounded it up. This is the best answer. That's the correct answer. Okay, all right, let's do a little exercise. We've got a few minutes. Let me just check just how many minutes we have. Oh, yes. All right. Put yourselves in groups of 3-ish. 3 should do. Let's have one person and one person only be the person that writes on the paper. So it just limits the amount of people that touch the paper. So one person is the designated scribe, and the rest of you are going to solve the puzzle that we're about to put on the board. When you turn in your answer, write your name plus the names of the people who are in your group on your page so you can get credit. There is a micro credit associated with this, but we're going to do this multiple times during a term. And before you know it, all of that adds up to like the amount of one quiz. Okay, can I ask you a question? You're going to have to think in order to do this. Question. A block of metal has dimensions of 1 centimeter by 2 centimeters by 3 centimeters. Okay, 1 centimeter, 2 centimeter, 3 centimeter. It has mass of 115.8 grams. Is it gold? The density, lowercase d, of gold, subscripted AU, AU is our elemental symbol for gold, is 19.3 grams per milliliter. Okay. And then here's the thing to remember from day 2 of class. 1 cubic centimeter is equal to a milliliter. Go. You can fill the room with noise, talk it out amongst yourselves, but let's just have one person be the scribe. Write the best answer down that you can. Make sure that you.
As good as it gets.
Yeah.
I don't know. I mean, I can move my fingers, but I can't.
Let's not.
There's a question like this.
Would this be set up right so my great grandchildren here?
The mass
is 115.8.
All right, we're almost running out of time.
Okay, yeah, so you don't do that to the answer, it'll just be that. It'll just be that, and then we're gonna like convert it.
It's already in milliliters, so cubic centimeters. I don't got a calculator yet, so. Doesn't have to like even do. I don't want to.
Yeah, it's like, it's just, I don't know, I know. So it's that. Well, I can't chemistry.
Take away from this.
So, the point of this is we're converting percentage to percentage. So it's always gonna be like, whatever you're gonna want it to be the same. As that, so you're gonna cancel it out. And since we're converting to milliliters, that's what you'll know on the top. Perfect now. I'm writing my notes that I
All right, we're good. Don't want to keep you over time. Make sure your name is on this. Friday.
Just want to have my name or.
And everybody's in.
You actually know what to do. Yes, I'm saying yes. I can do it. Yes.
The answer is, of course, yes, it is gold.
Remind me of what happened.
I had three.
And we're leaving.
All right. Okay. Well, good luck to you. Yeah, just keep check of
just like,
backwards. I think you should be okay.
I don't know, like, yeah, you're inserting, something or something, and you have to use that in order to